Section 9.3, Molecular Shape and Molecular Polarity. Now we have a sense of the shapes of the molecules adopt and why they do so. We'll spend the rest of this chapter looking more closely at the ways in which electrons are shared to form the bonds between atoms and molecules. We'll begin by returning to the topic that we first discussed in Section 8.4, namely bond polarity and dipole moments. Recall that bond polarity is a measure of how equally the electrons in a bond are shared between them, the two atoms in the bond. As a difference in the electronegativity between the two atoms increases, so does the bond polarity. We saw that the dipole moment of a diatomic molecule is a quantitative measure of the amount of charge separation in the molecule. The charge separation in the molecule has a significant effect on physical and chemical properties. We'll see in Chapter 11, for example, how molecular polarity affects boiling points, melting points, and other physical properties. For a molecule that consists of more than two atoms, the dipole moment depends on both the polarities of the individual bonds and the geometry of the molecule. For each bond in the molecule, we can consider the bond dipole, which is the dipole moment that is due only to the two atoms in that bond. Consider the linear carbon dioxide molecule, for example. As shown in Figure 9.11, each carbon-oxygen double bond is polar because the carbon-oxygen bonds are identical. The bond dipoles are equal in magnitude. A plot of electron density in the carbon dioxide molecule shown in Figure 9.11 clearly shows that these bonds are polar. On the oxygen atoms, regions of high electron density, red, are the ends of the molecule. On the carbon atom, regions of low electron density, blue, are in the center. But what can we say about the overall dipole moment of the carbon dioxide molecule? Bond dipoles and dipole moments are vector quantities. That is, they have both a magnitude and a direction. The overall dipole moment of a polyatomic molecule is the vector sum of its bond dipoles. Both the magnitudes and the directions of the bond dipoles must be considered when summing these vectors. The two bond dipoles in carbon dioxide, although equal in magnitude, are exactly opposite in direction. Adding them together is the same as adding two numbers that are equal in magnitude but opposite in sign, such as 100 and negative 100. The bond dipoles, like the numbers, cancel each other. Therefore, the over dipole moment of the carbon dioxide is zero, even though the individual bonds are polar. Thus, the geometry of the molecule dictates that the overall dipole moment is zero, making carbon dioxide a nonpolar molecule. Figure 9.11, carbon dioxide, a nonpolar molecule. A. The overall dipole moment of the molecule is the sum of its bond dipoles. In carbon dioxide, the bond dipoles are equal in magnitude, but exactly opposite each other. The overall dipole moment is zero, therefore, making the molecule nonpolar. B. Electronegativity or density model shows that the regions of higher electron density, red, are at the ends of the molecule, while the region of lower electron density, blue, is at the center. Now let's consider water, which is a bent molecule with two polar bonds. Again, the two bonds in the molecule are identical, and the bond dipoles are equal in magnitude. Because the molecule is bent, however, the bond dipoles do not directly oppose each other and therefore do not cancel each other. Hence, the water molecule has an overall non-zero dipole moment. Its dipole moment is 1.85 dynes. Because water has a non-zero dipole moment, it's called a polar molecule. The oxygen atom carries a partial negative charge, and the hydrogen atom has a partial positive charge, as shown in the electron density model in Figure 9.12. Figure 9.12, the dipole moment of a bent molecule. A. In water, the bond dipoles are equal in magnitude, but not exactly oppose each other. The molecule has a non-zero dipole moment overall, making the molecule polar. B. The electron density of the model shows that at one end the molecule has more electron density, the oxygen end, while the other has less electron density, the hydrogen. Figure 9.13 shows examples of polar and nonpolar molecules, all of which have polar bonds. The molecules in which the central atom is symmetrically surrounded by identical atoms are nonpolar. And the molecules which all the atoms are the same containing symmetrical atoms, linear, trigonal planar, tetrahedral, and square planar, trigonal bipyramidal, and octahedral, must lead to nonpolar molecules even though the individual bonds be polar. Figure 913, molecules containing polar bonds. Two of these molecules have a zero dipole moment because the bond dipole cancels out each other while the other molecules are polar.